Good day, and welcome to our webinar speaker series, hosted by the International Society for Industrial Ecology. My name is Preeth, and I will be your host for today's webinar titled Towards a Common Language and Data Structure for Resource Management. The ISIE webinar series invites leading practitioners and researchers from various subject sections to talk about the latest developments in industrial ecology. In today's webinar, we will learn from the Socioeconomic Metabolism section with our speaker, Professor Daniel Muller. Daniel Muller is a professor in industrial ecology at the Norwegian University of Science and Technology. He received an MSc in rural engineering and a PhD in technical sciences from ETH Zurich. Prior to his appointment at NTNU, he was a postdoc at TU Delft and an associate research scientist at Yale University. He was the lead author of the 5th assessment report of the Intergovernmental Panel on Climate Change, the Working Group on Mitigation. He served as a council member of the ISIE and co-founded the ISIE section, Socioeconomic Metabolism. He was a member of the steering committee of the Swiss National Research Program 65 New Urban Quality. Before we begin, we would like to remind our listeners that we welcome any questions you might have, and our speaker will answer them at the end of the talk. Please type questions directly into the Zoom Q&A window. You might see a little box at the top or the bottom that says Q&A, and once you click that, you'll be able to send in a question. And with that, we welcome Daniel to the ISIE webinar series.
Thank you very much, Preeth. Welcome, everybody. I would like to talk today about the need for a common language and data structure for resource management. The idea of this talk is not that I'm going to present you final results. It is much more an idea for how we can collaborate more effectively within the ISIE community, but also with industry and government organizations. So I start with a motivation and then point out how we currently use material flow analysis. We essentially create gaps that include hidden gaps. And in order to exchange data, this is not a very effective approach. And so I would like to introduce an alternative approach, which I call maps with explicit gaps. And then quickly introduce you to the MinFuture project and show you what we are planning to do. And then I hope we have some sort of a discussion as far as this is possible with just written questions. So I have to check now. It doesn't. Yeah. Okay. So I would like to start with key drivers for the socio-economic metabolism. So on the one hand, we have population growth and urbanization, industrialization. And what this is doing, it is essentially moving materials from the ground into products in use. A second key driver is globalization. Our value chains become much more specialized and sophisticated. And what this is doing to the socioeconomic metabolism, it is moving materials around the world. And the third driver is climate change and sustainable development. And here it is actually no matter whether we take measures for climate change or towards more sustainable development or not, we will always have consequences. We will need, in any case, new infrastructures and also changing global production and consumption patterns, whether or not we are taking action. If we take action for climate change mitigation, we need new energy systems which require lots of new kinds of materials, often scarce or critical raw materials. If we do not take action, we might need new infrastructures for hosting people that are migrating from countries where there are droughts or protect us from rising sea levels. So what we need essentially is a kind of a systems perspective. I have here a very crude overview of the socio-economic metabolism. You see in blue the energy flows, where we are mainly dependent on fossil fuels from the lithosphere, going to energy industries and then into the different energy consuming sectors. And we have greenhouse gas emissions from the consuming sectors, but also from the energy industries, which is mainly the electricity sector. What is important to see here is that these energy flows are not isolated. So the different processes for energy use and energy consumption, they are linked with each other through material flows. And this means that whatever actions we take to mitigate climate change, we always have impacts also on the material cycles. And as a consequence, we have secondary effects also on energy use and greenhouse gas emissions. And they can go in any direction. So it is very important that we understand the total metabolism, how it works, in order to guide us in the right direction. What we can say so far is that this socio-economic metabolism shapes the quality of our life. And it is doing so in two ways. First, it provides us with stocks in use, which are our transport system, they provide shelter, our infrastructure for education, for hospitals, you name it. On the other side, our quality of life is also determined, of course, by the quality of the environment, which is also changed through this metabolism. A second point that we can say today is that this current socio-economic metabolism is not sustainable. And it is not sustainable also for two reasons. On the one side, we have a problem with the in-use stocks, where we have poverty and inequality, where a lot of people still have a lack of access to essential infrastructures. So essential infrastructures to water, to energy, to transport, or shelter. On the other side, we have a problem of resource depletion and limited sinks for pollution, like, for example, climate change, or that we are filling lakes and the ocean with toxic substances. In order to reach a sustainable development, we therefore need a transformation of this socio-economic system. And this is a very big task. So far, we have a lot of engineers that have cleverly developed technologies that solve problems for individual processes, individual technologies that satisfy the needs on a small scale. However, if we scale these technologies up, we have, of course, large system effects, and we have so far not really procedures in place how we can guide also the largest systems that we want to control. So we need, therefore, to come from a design of processes and of individual products to a design of large systems. It's always a co-design that is needed. We need new processes, new products, but at the same time, we also need to control the larger system. So far, we are not even able to really understand how these cycles look like, let alone how to change the whole metabolism into a desired direction. So this is a very big task for this coming century. So it is important to see that this socio-economic metabolism is a shared system. We are all part of this. Every institution, everybody is part of this system. So everybody is participating in the socio-economic metabolism just by breathing and eating and housing and transporting. And also every institution is exposed to its consequences. It has consequences for our lifestyle, our well-being, for the environment, for jobs. And it also everybody and every institution is contributing to its change. Whether we want to have these changes or not is not matter. We cannot escape to be part of it. As a consequence, another aspect is that every institution or everybody understands their own part best, but all can benefit from understanding a better understanding of the context of the larger system. This is particularly so for companies who need to develop strategies, how they are positioning themselves in changing global material and energy flows. But it's also for governments who need to develop strategies for climate change mitigation, or for ensuring that their companies have sufficient access to resources. It is important to see that also everybody and every institution depends on others to reach their own goals. So we cannot say, we can reach our goals independently of what the others do. We are all codependent. So it is really a shared system. And this means that we need cooperation in order to monitor, but also to control the socio-economic metabolism. I would like to come now to the situation of the European Union to show you a little bit how governments react to this changing environment. In the case of the European Union, we have this so-called raw materials initiative, which should enable companies, or ensure that companies have unhindered access to raw materials in the future. And this raw material initiative is based on 3 pillars. The first is fair and sustainable supply of raw materials from global markets. What this is essentially addressing is the domain of international trade. So we need to understand where different countries get their resources from. So we need to understand international trade. The second pillar is sustainable supply of raw materials within the EU. And this is mainly addressing the domain of primary resource supply within the EU. And the third pillar is resource efficiency and supply of secondary raw materials through recycling. And this is addressing the third domain of secondary resource supply. Now, the challenge is that there is a lack of robust tools and data that would allow policymakers and industry to see how demand and supply are changing, how their boundary conditions are changing, but also to test different strategies, how to position themselves with these changing boundary conditions, to set priorities, but also to integrate these 3 pillars, strategies for these 3 pillars. So the European Union has formulated and detailed strategies for what can be done within these 3 domains. However, there is actually a lack to see how these pillars are actually also linked with each other, how one can influence the other, and how one can make the other one potentially also obsolete. So what is really needed is a system approach that integrates these 3 domains. And the most basic level that is needed is actually just understanding the stocks and flows of resources. And this is what we are trying to address in this, as this is one of the aspects that we are trying to address in this MinFuture project. So what we are trying to do in this MinFuture project is essentially a proof of concept for a Google Maps of the global physical economy. So we would like to understand in the long term the global physical economy in terms of on multiple scales, and to really be able to see where we are today and develop scenarios where we could go into the future and what this could involve. The motivation for this is largely based now on the critical raw materials discussion. It is about securing access to raw materials as they are critical for many countries and industries. And the solution for this is that these strategies for ensuring sustainable supply of raw materials, they need to be informed by a robust understanding of global material cycle. So it's not enough that the EU is just looking how they are managing their materials, and the US and India and China are doing it for their own countries. All have an interest to understand the global cycles and the role that they are playing within the global cycles. The barrier that we are facing today is that the knowledge about these global material cycles is highly fragmented. And it varies significantly by mineral, by stage of the supply chain, by country, and so on. So there is a significant lack of a common language, in addition to a lack of data also that needs to be filled. And we are addressing now mainly this lack of a common language. And the way how we try to overcome this barrier is by integrating the existing knowledge in a common approach to material flow analysis and through international cooperation. So the purpose of this MinFuture project is to establish an international platform for MFA. This consists of key data providers, of data users, and research institutions. And the development of this common language is done, the most essential part of this common language is essentially the data structure that is below the data that can be exchanged later. In our consortium, we have a wide variety of universities, many of which you might know as colleagues from industrial ecology. We have also several geological surveys being part of it. And what is interesting is that we have also international partner. Even though it is an EU project, we have partners from Japan, from the United States, and from Australia. And we have also quite a high-profile advisory board with Magnus Eriksson from Luleå University of Technology. He was developing the largest database on a company-by-company basis for mining and production. Then Nedal Nassar from USGS, Christian Hagelücken, Umicore, Johannes Driels from Euromine, Stefan Bringitzer from the former Wuppertal Institute, Karin Hanghoy is leading the KIC of the EIT raw material. This is where all of the industry in Europe are kind of gathered within this European innovation platforms on raw materials. Then Ronald Janssen is Vice Director of UN Statistics, leading the Comtrade database for international trade. And Sigurd Heiberg from Petronavit. Sigurd was for many years leading UN institutions that were looking into the primary resource classification. And in addition, we will probably have Konstantin Ciupaghia from the Joint Research Center of the European Commission, which will be confirmed hopefully then in the next General Assembly. So we have a high-profile advisory board that allows us to really reach out to industry and government institutions. So as you know, usually in an MFA, you are probably all familiar with this. We start with a system definition that integrates all of the relevant parts, physical stocks and flows. This can look something like this. And then we are taking a second step. We develop a model for demand and supply forecasting. And in order to do this, we are assuming certain drivers that are acting on the different processes or flows. And we may develop indicators. And then as a third step, we are developing scenarios in order to address relevant questions. And in order to develop scenarios, we need to understand how these drivers are actually affected by changing boundary conditions, where we assume we cannot really change them. We assume that they are kind of given. And then by strategies, where we assume that we have a potential to influence. And of course, also by the problems as they are perceived and the goals that we are setting. So this is then informing the drivers. So you're probably all familiar with this. And the mean future is essentially trying to address all of these stages here. And we have partners from geological surveys that have more information on the lithosphere. We have UN statistics, Comtrade involved on the trade data. We have metals associations. Then we are trying to link us to the EU, US, Japan trilateral conferences on critical raw materials. Also, this project was actually initiated to support also these trilateral conferences. And therefore, we have also Japanese and American participants. And in addition, we have a lot of projects within the EU and of course also international that are addressing resource problems, mainly in the ground, but then also for project in use, products in use. The so-called ProSum project is prospecting secondary resources of the urban mine. So we are trying to include also aspects of these projects. In addition, we have other projects going on in the EU and other global initiatives that we are trying to take with as far as this is possible and meaningful for this project. So in this project, we have 6 work packages, and important are now the work packages 2, where we look at challenges, systems, and data. Then the work package 3 with models, and then the 4 where we have pilot cases, where we develop then also scenarios, and the work package 5 where we develop recommendations and a roadmap how to go on with this idea of developing a common language. And what I'm focusing now is mainly the work package 2, because that is what is kind of essential for establishing a common language, or is the most fundamental aspect of a common language. And for this reason, I would like to kind of show you how I understand how the information flows of the socio-economic metabolism has historically worked and how it is now, and how I imagine will happen in the future. So currently it is very much so that it is research institutions that are conducting socio-economic metabolism analysis. So they are developing these models, and they are using this data that they gather from industry association, from intergovernmental organizations like the UN or from the European Union, and from individual governments. So these institutions, they are essentially collecting data and then provide them publicly. But they are not really the original sources of the data. They are all also these institutions are collecting data from individual companies and also from private households, which are the original data providers. So this is how it works currently. So we have kind of, the flows are essentially just moving up, and it is just research institutions who are developing this SIM analysis, and then of course distributing this information. But we have, of course, also problems that different research institutions use different approaches for the socioeconomic analysis. Anyway, what I think in the future will be the case is that all need to have an understanding of this socioeconomic metabolism to one or the other extent. And it's not that everybody needs to have all of the details of everything, but there is an increasing need that companies need to understand the changing contexts within which they are operating, and they have, through their industry associations, an interest to better understand this. Also, governments have to position themselves always new in the changing environment. And even private consumers have an increasing interest to be informed about what they are consuming and how they can contribute towards changing the socioeconomic metabolism in desired directions. And the exchange of information is actually going in all kinds of directions. So it is not that the research institutions are in the future kind of the main hotspot. I see actually much more a tendency that this understanding is now being developed in research institutions, but the goal of MinFuture is not that we can build a monopoly. It's actually exactly the opposite. The goal of the MinFuture project is that in the future, intergovernmental organizations, industry associations, governments, and also companies are actually starting to apply these principles of systems understanding, and also that the data collection is happening accordingly. Latest trends in this information flow. So there are already trends that intergovernmental organizations are starting to pick up this kind of systems thinking. And this is very well illustrated with the example of the UNEP International Resource Panel, which has published several reports on resources and also has established a database for global material flows. So this is a very good example how there is a strong interest to have this knowledge not only accumulated in research institutions, but that it is penetrating other domains. I would like to illustrate another one with industry associations together with companies. In the case of aluminium, we have worked in the last years with the International Aluminium Institute and with several aluminium companies in the development of an information system of a global aluminium mass flow, which you can look on your own at the website that is indicated below. But I would like to show you quickly how this works. It is an animation that we have developed together with a professional designer. And with the International Aluminium Institute. So this graph here is illustrating the global aluminium cycle, and it has also a temporal aspect. So this the world is divided here into 10 different regions. Maybe you remember that China is blue, Europe is red, North America orange, and rest of producing countries, and the rest of Asia green. So we can now go back to 1962 and look how this has changed. I press now the start button, and you can see how at the beginning not so much is happening, with the orange one, North America being really dominant, and then later Europe picking up, even though at the beginning of the chain, rest of the producing countries are also quite important, particularly Australia. North America becoming more dominant, China still completely irrelevant, end of the 90s, and now China is starting to develop. You see that we have a lot of scrap flows here from industrialized country, but China growing very rapidly and very little scrap flows here still. And in the last years, China is growing per year with annual production rates of almost Europe. So incredibly fast how the change is happening. So this is kind of a fancy animation, but it is important to see that there are something like 70 million data records behind this animation, and that we can zoom in much more detail. I cannot illustrate this now, but it is sometimes more refined information that can be very relevant for industry. And the aluminium industry really has realized that understanding how the global cycle works is actually very important, not only for marketing and kind of showing that they are doing a lot of recycling, but mainly also for developing strategies. So for example, Hydro was realizing that there is a future business opportunity when they are investing in the scrap recycling, because we will have big problems with the scrap recycling due to quality issues if we are not starting with a sorting industry. And Hydro purchased about 2 years ago one of the leading companies in the development of sorting technology for recycling. So this shows that these kind of pictures are quite relevant also for companies, in order to understand how they can position themselves. Then further reflecting a little bit, what would it mean if we collectively develop an understanding of this global map of all kinds of materials and energy and emissions? Questions that are arising are, who is actually collecting what kind of information? Yeah? And who is sharing information with whom? And this leads to a question then, who owns actually which kind of data? What should be public? What should be private? Since everything is connected, there is of course also a lot of interest from the public to have some information about private activities, even though this is of course not the interest of companies who need to compete with each other. And another important question is, who is actually generating these maps? Today it is research institutions. Is this meaningful that research institutions in the future also do this? Or could it be better that individual governments are doing this, or industry associations as they have started? Or would it be the task of the United Nations or any other institution to actually collect this information and also harmonize the data? And with this, we come to the fourth question, which is now the most important for our project, which we are trying to address explicitly. How can the map making be facilitated? But in order to say how we can facilitate this, we first need to understand what's actually the problem. Yeah? What's the problem with the map making? And we have today several challenges in the monitoring and reporting of the global socioeconomic metabolism. First of all, there is a lack of system understanding by the modelers. So the researchers often have insufficient insights into a lot of details that can be relevant. And this means that data are often wrongly interpreted. Even if they are available, they are wrongly interpreted due to a poor understanding of how systems actually work. A second, oops. Yeah. I have now a problem here. There should be a second point, which is that there is a lack of system understanding also by companies and by government institutions who are collecting data in unstructured ways, and who are also challenged with the question of how to develop strategies. And they also have often a better understanding of their system, but they are not familiar with the material flow analysis language. And so this is a second challenge. Then a third one is that we have a lot of data gaps. And the usual way to handle data gaps is that we are just showing them on an aggregate level. We have a lot of data inconsistencies, differences in reporting. This is on all levels. So, for example, in Europe, the different geological surveys, they are all reporting their resource stocks and flows in different ways. And there are big efforts now going on to harmonize this reporting so that we have actually a consistent overview just within Europe, just to show you a little bit of the difficulties that we are facing here. And this is, of course, also leading to issues of wrongly interpreting the data, or that we need to aggregate strongly in order to really be safe in our conclusions. And then we have poor data quality, which leads to uncertainties. And we have also a lack of a common data structure. And this is limiting an effective exchange of data. So there are different projects trying to address this last point. And what we are doing is that we feel that we are, also the solution for the number 6 can only be done in an effective way if the points 1 to 4 are addressed. Now it's coming. Yeah. Okay, sorry for this mistake here. I would like to illustrate this now with this picture of the different stages of the aluminium cycle. This is a study that we have conducted with us, and the purpose of this is not to show you that this should be the right way to do it. It's actually exactly the opposite. I would like to illustrate that we have done the best as we could so far, but I would like to illustrate that we have several critical things that need to be addressed in the future. So we have a situation where we have statistical data being available. They are in blue. Then we have other data that we can kind of derive from coefficients. We have lifetime models in violet, and we can also kind of make estimates by using the mass balance principle, and sometimes we don't have data at all. But we still have challenges. So it is that we have, as I mentioned before, insufficient understanding of the system, and the meaning of the data from statistics are often poorly interpreted. Production and trade data are not harmonized, and we have limited data availability. And what we are often doing then is that we are using aggregate systems, and this leads to a situation where the system may not really represent the reality. And I would like to illustrate the same thing also in a different way. Traditional approaches to MFA have been that we are using some sort of a standard system, and we apply this to a new metal, and we try to see how can we place data that we find from statistics in these systems. So I would like to illustrate this now with a very simple example of the USGS extract of the minerals yearbook for aluminium, and with one of these standard systems that you are all familiar with. And I would like to illustrate it now just with one flow. So we have the flow from production to manufacturing, and we have statistics that are available. And the statistics have, for example, production, primary, and secondary. Is it this one that would go there, or is it the sum of both that would go there? The problem is that the secondary production of aluminium always uses also primary. So there would be some double counting that would not be accounted for. Then there is the apparent consumption. What's then the difference between the production and the apparent consumption? They are very different numbers, but what the manufacturing industry is consuming looks like the same arrow. Then we have other issues, that we have stocks of industry stocks, or we have stocks in the London Metal Exchange, and we don't really know how we can place this data. And what we are usually doing when we are developing material flow analysis on a more aggregate level, which is often necessary due to very poor data availability, then we develop crude maps with hidden gaps. So these systems often do not really reflect the reality of the data that are collected. Yeah? So these aggregate systems, they can be very useful to get a first overview. Yeah? So this is better than having nothing, is to have a very crude first overview. But the problem that we are facing here is that the data that is collected carefully by USGS in this case, the value of this information is somehow lost. Even if we get the right order of magnitude and can put a crude number there, there's a lot more information there that is kind of not included in these crude pictures that we are using. And what we are proposing is an alternative approach to MFA, where we are defining the system to fit the data as they are reported. And I would only like to illustrate now a kind of a little bit on one end how we might be able to do this. We need to have a much more refined system. This is now only showing the aluminium smelting with the electrolysis, and then the primary ingot market, and then the rolling. And each company, they always have inventories for products that they are using as resources, and they have inventories also of products that they are producing. And then they are going onto the road, or they are shipped. And on the market, we have also some part of the metals are always on the road, or they are in stocks, such as a London Metal Exchange and so on. So a more refined system allows us to say, okay, primary production, this is now this, and the production is the number here. And this number is different from the shipment, what is going out. And secondary production we don't have, and apparent consumption is actually something that is quite far away from this one here. That's why we can have such a big difference. And we can also look then at the industry stocks. They are here, and the stocks that are on the way. So we see now that these inventories of industry, they are in this case quite large. They are larger than an annual production. So it could be very well that if we just have data on the production, and we assume, yeah, they are probably roughly what is actually also shipped, that we may make quite a large mistake here. Even though we may not have the information on what is actually shipped. So we call this approach refined maps with explicit gaps. And the idea is that these refined system definitions can be made to reflect the exact location of the measurements. So the idea is not that we can have complete cycles represented. That's like a later state. It is just reflecting the data that are reported in the most accurate way. And this is resulting in gaps, of course. We do not know, for example, this flow here. But it's making the overall models more robust because we can easily make such an assumption that these stocks are not changing. But we have to make these assumptions explicit. However, developing such a refined system definition requires a knowledge that goes far beyond what we know in research institutions. And this means that we need to work together with geological surveys and also with companies that are actually out in the business who have a much better understanding of how the things actually work. Even though they might not have the understanding of the systems approach that we are using. I would like to show this in a different way. It is very similar like maps. I started originally saying that it's like Google Maps, and I would like to make this analogy again. If we are developing maps, there are always two things that are needed. The first thing is we need a georeference. We need a coordinate system. We need to know if a point is measured in the landscape, we need to know exactly where it is. And then we can collect all kinds of information related to this point. We can measure the height that it has. We can measure the vegetation, the temperature, whatever you like. This allows us then to create maps once we have several relevant points and we can interpolate them to develop maps. And this is actually very analog to creating maps of the socioeconomic metabolism. It's just that instead of a coordinate system, we have kind of a metabolic system that is serves as the background, which needs to be defined. And then we have, again, layers that can be added to all of the different flows. We can measure, in this case, the production or the shipment of alumina. We can measure the value, we can measure number of units, total mass, we can measure the aluminium within them or other elements. It's of course an indefinite number of aspects that can be measured and then also mapped about these flows. But the essential point that I would like to make is that maps are only as good as not only the measurements are, but also where we know where the measurements are actually taking place. And this means the system. They go together. And so what we are doing in this work package is that we are trying to add coordinates or system definition to the values published. And we do this not as a research project alone, but we would like to do this through case studies together with different stakeholders. And we are looking at different dimensions that we try to integrate. We look at different stages. We look at how to integrate trade in a consistent way. There are a lot of issues related to harmonization between trade and production data. We are looking at the linkages of metals using this layered principle. And we are looking at the dimension of time, so historically and also for the future. Next steps that we are taking is that we develop a first refined map with explicit gaps for aluminium. And we do this in cooperation with different geological surveys and also with the JRC and with industry and UN statistics. The goal here is that we are placing all of the statistical data on aluminium available in adequate systems. And this is helping us to develop a common learning process. So we are providing more the understanding of the material flow analysis, and others are providing us with a real-life understanding of the system, and we hope that the two are matching so that we can actually reflect not just our more overview cycles, but also the actual data, how they are measured with their exact locations. The ambition here is that USGS and other geological surveys will use system approaches for monitoring and for publishing their data. That in the future, the Minerals Yearbook is not coming as a table, or maybe it's still coming as a table, but that the table is understood in a way that we know exactly what the different numbers actually mean with the use of a system. And as a second step, we are developing a first generic data structure, and we do this in collaboration with Yale and USGS, who currently have a project that aims at storing all of the data that the group of Tom Gradle has produced over the last 15 years in a database and make this available for USGS and also for the public. So they have a project that has kind of a similar but also complementary goal, and we work together in this project to see how we can support each other with this. Also, the ISIE has an effort to harmonize the data collection and make more transparent, particularly also data that is published. So we are in contact with Stefan Pauliuk on this, and we would also see that we can harmonize this. In addition, we would like to connect us with other larger efforts to track global material flows, such as the UNEP, IRP, OECD, and Eurostat, to see in how far they could benefit from how we could support them in their effort by providing a system basis for the professional data providers when assembling then these global flows. As a third step, we are developing additional refined maps, and we are going to do this also on a company level. So we are cooperating then with individual companies and also with geological surveys. Geological surveys often send out questionnaires to companies who fill then in the data, and neither these questionnaires nor the companies use then systems. And we would like to investigate whether system approaches for companies and geological surveys that are harmonized could support both of them in the long term and make the whole procedure actually much more simple. The goal here is to select companies in the monitoring of their metabolism. And the ambition is that companies will use system approaches for monitoring and reporting of their data. So we'll see whether we succeed with this, but we would like to use different companies to see also where we are succeeding with this approach. And this is then leading to also a refining of the data structure, where this then from the company to the association to the government and hopefully then also that we can connect us with some of the other efforts to develop global databases, that we can kind of show how this could be made much more easy and machine readable once we are able to mirror the systems of the data collectors. And then the next step is to develop a roadmap for mineral resource data management, where we have several workshops taking place over the next years in order to see what could, this project is more an initial start, and we would like to see then how could this idea of collaborative development of an understanding of the global metabolism could be brought further. So I would like to thank you for your attention, and I would be happy to receive questions. There is one thing that I would like to add, and that is in case that you are involved in any project with a similar goal, be it to develop kind of a common database or a common data structure. It can be on a large scale, it can be on a small scale, or it can be on specific areas. Then please let us know. The goal of the Min Future is, as we mentioned at the beginning, not that we can kind of monopolize this. It is much more that we can develop something more of a language that would support all of the people who are interested in collaborating.